the schedulers. Okay, so not the different types of the schedulers. The schedulers, they are responsible, it's part of the operating system process manager, so which manages the processes. Okay, so part of the operating system, scheduler is part of the operating system which is responsible for scheduling processes to the central processing unit. So the scheduler category which is responsible for that activity is called the short-term scheduler or the CPU scheduler. It selects which process should be executed next and allocates CPU to that process. So if you remember from the discussion in the last class, when you try to execute a process or when you instruct the operating system to execute a process, the process your program would be loaded into memory and it becomes ready for execution. So ready for execution doesn't mean it has already started execution, right? So after that, so there may be at any point of time multiple processes which are ready for execution. And the scheduler or the short-term scheduler, which we call it right here, short-term scheduler. So at any point of time, there may be say n number of processes. And depending on certain criteria, it chooses the next process, uh, and the next process to be given the central processing unit (CPU). Okay, so short-term scheduler selects which process should be executed next. Which process should be executed next, right? Sometimes in this is the only scheduler in a system. I mean the category of scheduler. So a scheduler which selects a process to be executed next. Short-term scheduler, the name is given because it is invoked very frequently. So in terms of milliseconds. Okay, so it is invoked very frequently. Compared to that, if a system has long-term scheduler or job scheduler, it selects which processes should be brought into ready queue. So if you remember that state transition diagram, so we had this new state. From new state, the process is brought into memory. This is ready state. From ready state, it goes to run or execute state. Okay. Then when the running is over, it goes to finish state. And if it has to wait for certain event, then it goes to wait state. If the wait, when the wait is over, then it goes to ready state again. So this long-term scheduler actually comes into picture here. From new state, a long-term scheduler selects a process among those processes which are currently in new state and brings it into memory for execution. So thus it becomes a ready state. So among the processes which are in ready state, the short-term scheduler STS comes into picture here. It selects a process among those processes which are currently in ready state and gives a CPU to that process, and that process actually executes here. So short-term scheduler is invoked much more frequently compared to the long-term scheduler. So long-term scheduler is invoked infrequently in terms of maybe say seconds or minutes, and long-term scheduler controls the degree of multi-programming. So at any point of time, number of say processes which are present in memory for execution is called degree of multi-programming. So at any point of time, if it is true, the long-term scheduler may find that the degree of multi-programming has reduced, so it will introduce more number of processes into the ready state. So it controls the degree of multi-programming, this long-term scheduler, right? Then these processes can be described either as IO bound process or CPU bound processes. Okay, the examples are in case of IO bound processes, they spend more time doing IO than computation. Okay, so the processes which spends more of its time doing IO compared to say computation is called IO bound process. For example, say interactive process or games, those are examples of IO bound processes. They require user interaction, frequent user interaction, right? So user interacts with those applications or those programs via some IO devices. So frequent IO events would be there in case of IO bound processes. Okay, and CPU bound processes in those are called CPU bound processes, which spends more time doing computations. Okay, so maybe say some number crunching application. Say you have written a program which will read, say, 1 million number from a file, and then it will compute or it will perform certain task over that 1 million number. Okay, so reading that 1 million number, assume that it takes 1 minute, and then it will perform that number crunching task. So that may involve say half an hour or 1 hour or maybe longer. So most of the time when it is doing operations of those number, it is actually using CPU. So it is not, most of its time it is not spending say waiting for the IO devices. So in this case we call them as CPU bound processes. Whereas in case of IO bound processes, the processes they spend most of their time doing IO. So long-term scheduler strives for good process mix. That means long-term scheduler tries to select those processes such that there is a good mixture of IO bound processes and CPU bound processes. If all the processes are all most of the processes are CPU bound, then their waiting time will be longer. If most of the processes are IO bound processes, then CPU may sit idle. Okay, so there has to be a good mixture of IO bound and CPU bound processes. Now, the midterm scheduler can be added if degree of multiprogramming needs to decrease at certain point of time. So we have seen this long-term scheduler is responsible for controlling the degree of multiprogramming. Long-term scheduler is responsible for controlling the degree of multiprogramming, right? So that means when the degree of multiprogramming reduces, it increases the degree of multiprogramming by introducing more processes into the memory, okay, into the ready state. But it may so happen that at certain point of time, the degree of multiprogramming may have to be reduced. Okay, so there may be certain reason for that. So in that case, the we have to remove process from memory, store on disk. That means currently, for example, say there are n number of processes in memory. They are executing, but due to some reason, the degree of multiprogramming, which is currently 5, has to be reduced. So this might be that one of the process is high priority process and it requires much memory or it requires more memory as compared to that.
Sir, your voice is breaking.
Hello, am I audible now?
Yes, sir.
Okay, so that midterm scheduler is responsible for swapping out a process from memory. Then when situation improves, then that process will be brought back into memory into that ready queue. Okay, so that is the task of midterm scheduler. So in some cases we might be having midterm scheduler. So we have short-term scheduler, long-term scheduler, and midterm scheduler. Okay, so when CPU switches from one process to another process, the system must save the state of the old process and load the saved state of the new process, and this is called the context switch. So, context switch is the event when CPU is switched from one process to another process, and this context switch during context switch, the activities are performed by the operating system. Okay, so it switches the context from one process to another process. The context of a process is represented in the PCB of the process control block. So as I have already told, each process is represented by a process control block in the operating system itself. So in operating system own memory area, each process is represented by a data structure which is known as process control block, right? So that process control block actually contains all information regarding the state of a process. So when CPU switches from one process, say process A to process B, then the context or the state of the currently running process A has to be saved in PCB of process A. And if process B had executed earlier, then the saved state of process B has to be restored from PCB of process B. So this is called context switch, and the time involved in that is called context switch time. And this context switching time is pure overhead. So this during this time the operating system is busy switching the context from one process to another process. None of the user processes they are currently executing. So system is not doing any useful work during this time during switching. For more complex OS and the PCB, the longer the context switch, say if the PCB content, if the definition of state of a process, it is more complex. So saving the state of a process, loading the state of a new process, it will involve much more time. So it will actually result in longer context switch time. So context switch time is dependent on hardware support. In some cases, the underlying processor has got some support in terms of additional hardware unit, which actually helps in reducing the context switch time. Like say this processor, Sun UltraSpark processor, it provides multiple sets of registers so we have set one, say register sets. So set of registers, say S1, another set of register S2. Okay, okay. So when process P1 was executing, probably it was using this set of register. And say in process P2, when the context has to be switched from process P1 to process P2, okay, it is not required that they say set of registers S1 has to be stored into say PCB or process P1 because we have another set of register. So P2 might be given the another set. So P2 would be using the another set of register. It's like say in a classroom we have two whiteboards, right? Say when teacher one is taking one class, that teacher one is using one of the whiteboard one. When the class finishes, the teacher one need not wipe out the whiteboard one because the next teacher may use the whiteboard two, so that when again teacher one will come back, resume his or her class, that teacher can use that whiteboard one, right? So the number of whiteboards you will be having that will actually increase the performance, that means that it will decrease the context switch time, right? So the Sun Ultraspark processor has got number of such register sets in the processor itself. So context switch simply requires changing the pointer to the current register set. So currently running process P1, it will have a pointer which points to the currently used register set, which is S1. When context switches from P2, then it will have a pointer. That pointer will point to this register set S2, meaning that P2 is currently using register set S2, and so on. Right? So this is one example where we have hardware support for improving the context switch time. Improving means reducing the context switch time. Right? So this is all about processes, how processes are managed. I mean, processes are represented in the operating system. So next we will see how exactly these processes are scheduled in a uniprocessor system.
স্যার পিসিবি কিটে অনেকটা পিএসডব্লিউর মতোই তাহলে।
পিএসডব্লিউ ছাড়াও আরো অনেক কিছু ইনফরমেশন থাকছে। পিএসডব্লিউ হচ্ছে প্রসেসর স্ট্যাটাস ওয়ার্ড। তুমি জানো নিশ্চয়ই প্রসেসর স্ট্যাটাস ওয়ার্ডে কি থাকে? হ্যাঁ, so processor status word একটা simply a register. It contains at that point of time status of the processor different. Say for example 8085 processor status word contains whether the result of the previous operation generated carry, whether the result of the previous operation was zero or non-zero, and so on, right? So that processor status word is part of the processor state. এইটা বললে প্রসেসর স্ট্যাটাস ওয়ার্ড সেভ করলেই কিন্তু প্রসেসের স্টেট সেভ হচ্ছে না। ইন অ্যাডিশন টু দ্যাট ওই প্রসেসটা ওই সময় কি কি ফাইল ওপেন করে রেখেছিল, ওকে, অন্য কি কি রিসোর্স ইউজ করছিল, সিপিইউ কতটা ইউজ করছে, যেটা আমি আগের দিন আলোচনা করেছি। সো অল দোজ ইনফরমেশন অ্যাকচুয়ালি ডিফাইন্স প্রসেস স্টেট and that is stored in PCB, right? Okay, so now I'll start this CPU scheduling in uniprocessor system. Okay, so the previous slide I have talked about this CPU bound process and IO bound process. Why at all we should have a good mixture of CPU bound process and IO bound processes. So in order to maximize the CPU utilization, often with multi-programming. Mind that. So we have this multi-programming concept, meaning that keeping in memory multiple programs for simultaneous execution. But in a typical uniprocessor system, there is no such concept of simultaneous execution. It's purely sequential execution. And this switching from one process to another process happens so fast that to the end user, as a human being, we perceive that our processes, multiple processes, they are running simultaneously. Okay, so so in this case, to have a mixture of CPU bound and IO bound processes, we assume that in this case, a typical process, it consists of processes execution consists of cycle of CPU execution and IO wait. So throughout its execution, so when it starts, say a process starts from here, it starts with a CPU burst. We call it as CPU burst. That means it uses CPU for, say for example, say 10 millisecond, and then it does some IO. Okay, so it may be say 4 millisecond. This is IO. Then it does again a CPU burst. So it's called CPU burst and IO burst. Say CPU burst of say 12 millisecond, then followed by another IO burst. So say IO burst of say 6 millisecond and so on. So this length, the length of the CPU burst and IO burst, they will be different corresponding to CPU bound job and IO bound job, and number of such burst CPU burst and IO burst they will also differ. So typically, so that scientific number crunching application that I told, probably it will consist of first whenever it starts with a CPU burst, then it will read numbers from a file. Say we will have a say 1 minute of IO burst. After that, say 1 hour of CPU burst. After doing the computation, after that it will write the result back into the file. So another IO burst, then finish. Okay, for CPU bound job, so if the total execution time is say, for example, say 1 hour 15 minutes, probably it will use CPU for 1 hour of time, so remaining time 15 minutes IO. So most of the time it will use the CPU. Whereas in case of IO bound job, whatever time it has been given, out of that time, most of the time it will be doing IO. Okay. So typical execution of a process, it consists of CPU burst followed by IO burst, CPU IO, and so on. Right? CPU burst distribution is of main concern. So what is the distribution of CPU burst lengths? So this length, what would be this? So it actually depends on the characteristics of the process itself, what it does actually, so what task it is performing. So based on that, actually this CPU burst length, distribution of CPU burst length actually depends on that fact. So the short-term scheduler selects from among the processes in ready queue and allocates CPU to one of them. You already know. So we have new state. Let's try to draw this again. So new state, this long-term scheduler brings one of the process which is in new state to ready state, and we have multiple processes in ready state, and short-term scheduler selects one of the process which are in ready state, and that process currently executes or in running state. Then this running state, that process may require some IO event, and it may have to wait. It will do a wait, and when the waiting is over, it will come back to this ready state again. And from this execute state, it will go back. So when this execution is over, it will go to this finish state, finish. And it may so happen that during execution, when it was executing, it may be interrupted and brought back into ready state again. Okay, so we'll look into this, and depending on whether a process can be interrupted or not, we'll have two categories or scheduling. So in any case, the short-term scheduler is responsible for selecting a process which is currently in a ready state, and then after a process has been selected, that process will be brought into this running state. Okay, we have in the ready state, one queue is maintained which is called queue of processes, which this queue is called a ready queue. In ready state, a queue is maintained that is called ready queue. So ready queue contains all the processes which are in a ready state. CPU scheduling decisions may take place when a process does this thing. So any one of these four events happen, then CPU scheduling decision has to be made, right? So let's see. So when a process switches from running to waiting state, so let's see here. When a process, so a process was executing right here, and from running state, it goes to waiting state. Running state, it goes to waiting state. So CPU is free right now. Okay, so short-term scheduler has to select one of the process from a ready state, which are in ready state, so that it can be given CPU. So that is case number one. When a process switches from running state to waiting state, CPU scheduling decision has to be made. Then case 2, when a process switches from running to ready state, so a process was executing right here and it was interrupted due to some reason and that process is brought into ready state. This is case 2. Okay, so in this case also a CPU scheduling decision has to be made because no process is currently running. One of the process which is in ready state, from that it has to be selected and given the CPU. Then when a process switches from waiting to ready state, when a process switches from waiting to ready state, right? In this case, a process was waiting, now it becomes ready. So when it becomes ready, it may so happen that at that point of time, no other process was there in the system. It was the only process which is currently ready. So a short-term scheduling decision has to be taken. So that process would be selected and it will be given CPU. Or it may show up in that the process which actually finished waiting and become ready has got the highest priority. So if the scheduling is based on priority and the currently running process has got lower priority, then this process would be interrupted. Okay, currently running process would be interrupted and the process which has just now from waiting to ready, it has come to this ready state would be scheduled. So this is the case 3. And when a process was executing and it terminated or it finished its execution, then none of the processes are executing, the CPU is free, then one of the process in ready state has to be selected. So these are the 4 cases in which the CPU scheduling decision has to be made. This short-term scheduler will be invoked in these 4 cases. When scheduling decisions are made in under circumstances 1 or 4, that means when a process was executing, it either went to do some IO operation or it actually finished execution. Okay, so if scheduling decisions are made only in these cases, that means when a process finishes or when a process goes for IO, that means when a process voluntarily releases the use of the CPU, if CPU scheduling decision is made only on these cases, in those cases, then we call it as non-preemptive. Other schedulings are called preemptive. Why preemptive? So this thing. So 1 and 4, so 3 and 2. So currently running process, it is interrupted due to some reason, and another new process would be scheduled. Okay, so preemptive means we are actually interrupting the currently running process and another process is scheduled. Premature empty. We are emptying the currently running process from using the CPU. We are emptying the currently running process from using the CPU prematurely. So that process hasn't voluntarily released. সে বলেনি আমার কাজ শেষ হয়ে গেছে বা আমি IO করতে যাচ্ছি. So that process was executing, but it was forcibly stopped and CPU was taken away from that process and it was given to other process. So that is called preemptive. So if scheduling is done in case 2 and case 3, then we call it as preemptive. Otherwise, it is called non-preemptive, right? So these are the 2 categories of short-term scheduling. Okay.
1 আর 2 এর মধ্যে স্যার ডিফারেন্সটা আরেকবার কাইন্ডলি বলুন। 1 আর 2
One,
মানে ওয়েটিং স্টেট আর রেডি স্টেট।
ওয়ানটা কখন হচ্ছে? হ্যাঁ, ওয়ানটা কখন হচ্ছে এক্সিকিউট করছিল, সেখান থেকে ও ওয়েটিং এ চলে গেল। কেন ওয়েটিং এ গেল? ওর কোনো আইও ডিভাইসেস দরকার, সেই আইও ডিভাইসটা হয়তো অ্যাভেলেবেল নয় কারেন্টলি। আচ্ছা, তাহলে সে যখন ওয়েট করছে তার মানে সে সিপিইউ ব্যবহার করছে না, তাহলে সিপিইউ শিডিউলিং ডিসিশন নিতে হবে, আরেকজনকে এখানে নিয়ে আসতে হবে। এটা বুঝতে পারলে 1 নম্বরটা। আচ্ছা, 2 নম্বরটা কখন হচ্ছে? একটা প্রসেস এক্সিকিউট করছিল, আমি তাকে ফোর্সিবলি স্টপ করে দিলাম। স্টপ করিয়ে দিয়ে তাকে আমি রেডি স্টেটে নিয়ে চলে এলাম। কেন, তুমি প্রশ্ন করতে কেন তাকে স্টপ করলাম?
হ্যাঁ স্যার, কেন কেন?
হ্যাঁ, বিভিন্ন কারণ থাকতে পারে। যে ধরো প্রসেসের যদি বিভিন্ন প্রায়োরিটি থাকে, ধরো এই ডক্টরের এক্সাম্পল যখন দেখছিলাম, যে ধরো তুমি একটা পেশেন্ট, তোমাকে হয়তো ডক্টর অ্যাটেন্ড করছিলেন, তো সেই মুহূর্তে একজন ইমার্জেন্সি পেশেন্ট চলে এলো। তখন কি হবে? ডক্টর তোমাকে প্রিএম্প্ট করবেন, মানে ডক্টর তোমার তোমার কন্ডিশনটা বুঝে তোমাকে বলবেন একটু ওয়েট করুন, মানে তুমি আবার রেডি স্টেটে চলে গেল। আর যে ইমার্জেন্সি রোগী যিনি এসেছেন তাকে তিনি অ্যাটেন্ড করতে থাকেন। ওকে, সো দ্যাট ইজ দিস কেস, সো ইউড বি preempted. So based on your priority, maybe your priority process's priority is less and another process has arrived whose priority is high. So that high priority process would be scheduled and your low priority process would be preempted. বুঝা গেল? এটা হচ্ছে দুইটা যখন হচ্ছে যে একটা প্রসেস রান করছিল তাকে আমি ফোর্সিবলি স্টপ করে দিলাম। কেন করলাম? কারণ অন্য কোনো হায়ার প্রায়োরিটি কাজ আছে যেটা সিপিইউকে এখন করতে হবে। ঠিক আছে?
হ্যাঁ ঠিক আছে।
ওকে, so we have two categories of scheduling. One is called preemptive and another is called non-preemptive. So preemptive and non-preemptive, right? So scheduling category, preemptive and non-preemptive. Dispatcher module, okay. Now, what is dispatcher, right? Dispatcher is the model which gives control of the CPU to the process selected by the short-term scheduler. So short-term scheduler, it only selects the next process to be given the CPU. It only does the selection, but the actual, say, assignment of the CPU to that selected process would be performed by the dispatcher module. So dispatcher module gives control of the CPU to the processor. It is responsible for giving the control of the CPU to the process selected by the short-term scheduler. Okay, short-term scheduler selects the next process, and dispatcher module gives control of the CPU to the selected process. And this task involves switching the context, so switching the context from the currently running process to the selected process, switching to user mode, then changing the mode to the user. So user mode, the user processes, they run in user mode and the operating system run in privilege mode.
স্যার বলছি যে এইটা প্রিএমটিভ নন প্রিএমটিভ যেটা বললেন, এটা কি মানে অ্যাভারেজ ওয়েট টাইমটা মিনিমাইজ করার জন্য নাকি?
না, এটা প্রিএমটিভ নন প্রিএমটিভ ক্যাটাগরি যেটা,
হ্যাঁ,
সেটা হচ্ছে বেসড অন ইওর ওএস ডিজাইন রিকোয়ারমেন্ট। তুমি যে যে অপারেটিং সিস্টেম ডিজাইন করছো, ধরা যায় সেখানে
আগে যেটা বললেন ওই প্রসেস শিডিউলিং, হয়তো P1 P2 P3 এরকম প্রসেস আছে, তো ওটা মানে শিডিউলিং করা মানে কি, মানে ওটা সবকটার অ্যারাইভাল টাইম যদি আমি একই ধরে নিই, তো এরপরে মানে অ্যারাইভাল টাইমটাকে মানে আমাকে সেইভাবে শিডিউল করতে হবে যাতে মানে ওয়েট টাইমটা কম হয়, মানে এক্সিকিউট যেটা আগে করার কথা, যেটা মানে টাইম বাস টাইম যেটা কম আছে বা ওই
সেটা সেটা তো সেটার উপরে ভিত্তি করে, ধরো তুমি যে বলছো কথাটা বলছো বার্স টাইম যেটা কম আছে তার উপরে ভিত্তি করে, তাহলে প্রত্যেকটা বার্স টাইম আমাকে দেখতে হবে, তাহলে সেটা হচ্ছে শর্টেস্ট জব যেটা আছে তাকে আমি শিডিউল করব। তো সেইগুলো হচ্ছে ডিফারেন্ট শিডিউলিং স্ট্র্যাটেজি।
হ্যাঁ হ্যাঁ,
কিন্তু
তারপরে মানে যেটা মানে রাউন্ড রবিন সিস্টেমটা আছে,
ওগুলো এখনো আমরা আসিনি। ওইখানে আমরা দেখবো যে বিভিন্ন সেট অফ প্রসেস দেয়া থাকলে, তো আমরা বিভিন্ন যে শিডিউলিং স্ট্র্যাটেজি আছে তার উপরে সেইগুলো ব্যবহার করলে কোনটাতে কিরকম পারফরমেন্সটা হয়, রাইট? কিন্তু এখানে যে প্রিএমটিভ আর নন প্রিএমটিভের ব্যাপারটা, সেটা টোটালি কিন্তু আমার মানে ডিজাইন প্রিন্সিপাল, এখানে ওএস ডিজাইন প্রিন্সিপাল, যে আমি এই ধরনের জিনিস অ্যালাউ করব কিনা। যে ধরো তুমি বললে যে আমি এই ধরনের প্রিএমশন কোনো মতেই অ্যালাউ করব না প্রথম দিকে, তোমার কিন্তু মাথায় নেই সেখানে তোমার অ্যাভারেজ ওয়েটিং টাইম বা এই সমস্ত কিছু কমানোর জন্য বা এটা তুমি প্রথমেই ডিসাইড করলে যে আমার এখানে সেরকম হবে না, আমার এখানে যে ধরনের প্রসেস আসবে, যখন আসবে তাকে যদি আমি সিপিইউ দিয়ে দিই, তাকে সে যতক্ষণ না নিজে থেকে ছেড়ে দিচ্ছে ততক্ষণ আমি অন্য কোনো প্রসেসকে দিতে পারবো না। So in that case we call it as purely non-preemptive. ওকে, কিন্তু নন প্রিএমটিভ করলে ঝামেলা আছে। একটা বড় প্রসেসকে তুমি দিয়ে দিলে সিপিইউ, সেই বড় প্রসেসটা কাজ করতেই থাকলো কাজ করতেই থাকলো, বা এটা এমন হলো যে সেই প্রসেসটা একটা ইনফাইনাইট লুপে পড়ে গেল, তুমি আগে থেকে জানো না সে কতক্ষণ কাজ করবে, কিন্তু সে ইনফাইনাইট লুপে পড়ে গেল, তাহলে পেছনে যারা আছে অন্যান্য প্রসেস তারা সুযোগই পাচ্ছে না, রাইট? তো এরকম অনেক কিছু যদি আমার যদি ভয়েস আমার যদি প্রিএমটিভ থাকে, সেখানে যদি আমি একটা টাইম লিমিট করে দিই, ঠিক আছে আমি দিয়ে দিলাম, কিন্তু 5 মিনিটের বেশি হলে তারপরে আমি তাকে ইন্টারাপ্ট করব। ওকে, তো এটা ডিপেন্ড করছে এন্টায়ারলি তোমার ডিজাইন প্রিন্সিপালস এর উপরে। তো নরমালি এখনকার যাবতীয় যে অপারেটিং সিস্টেম আছে, সো দে অল ইউজ প্রিএমপ্টিভ শিডিউলিং। ঠিক আছে, তো আমরা ওই অ্যাভারেজ ওয়েটিং টাইম বা ওই সমস্ত কিছু সেইটা দেখবো, সেটা কখনো যখন আমরা দেখবো সেটা হচ্ছে তখন আমরা বিভিন্ন যে শিডিউলিং অ্যালগরিদম গুলো আছে সেগুলো যখন আমরা দেখবো তখন সেগুলো আমরা বার করার চেষ্টা করবো। So dispersion module is responsible for giving the control of the CPU to the selected process. So it does the context switching, then switching to the user mode. So after giving control of the CPU to the newly selected process, the mode of the processor has to be switched to user, then jumping to the proper location in the user program to restart the program. So newly selected the process আছে তার proper location আমাকে jump করতে হবে, because it might so happen that that process had executed earlier, so it would be resuming its execution, so we have to resume from appropriate area. Okay, so dispatch latency is called the time that is taken by the dispatcher module to stop one process and start another process. This dispatch latency should be minimized. Okay, so it should be as minimum as possible. Right. So the short-term scheduler selects a process among all the processes which are currently in ready state. So the scheduling criteria, based on which criteria it actually does that selection process. CPU utilization. So keep the CPU as busy as possible. So the scheduling algorithm will try to maximize the CPU utilization. Okay, so if the machine actually operates for 100 time unit, so our objective would be to keep it busy 100 time unit only. So the utilization would be 100%. Throughput is number of processes that complete their execution per unit time. So number of processes that complete their execution per unit time. Okay, so if the say machine is kept on say for 100 time unit, then the number of processes that complete their execution in unit time, so in 100 time unit, if say 20 processes finish execution, okay, the number of processes that complete their execution per time unit would be 0.2. Turnaround time is the amount of time to execute a particular process. Okay? So when the process actually entered into the system and when it actually exited from the system, that is called the turnaround time. Waiting time, the amount of time a process has been waiting in the ready queue or other queues. So those are called waiting time. Then response time is the amount of time it takes from when a request was submitted and until the first response is produced. Right. So this response time is what is this response time is not the first time when the first output is sent. Rather, this amount of time it takes from when a request was submitted and until the first response is produced. Okay, so it may swap in that in some cases. Let's take some example to understand this response time. In some cases, you have your machine is say probably you have opened number of windows, a number of applications are running. Your machine is heavily loaded, and now you require Microsoft Word. Assuming you are in Windows, and you clicked on that Word icon, double clicked on that Word icon, that means you have requested the execution of Word application. Okay, so that when you double click on that, that is the time when actually you requested an action. That is the execution of that Word application. And as the system was heavily loaded, you probably didn't get that say window of Microsoft Word immediately. Rather, it took some time. Okay, so the time difference may be 10 seconds or 20 seconds, or it may be even more. So that is the response time. The time that you have make a request and the first response you get, that time difference is called the response time. Okay, so if the response time actually increases, ধরো আমরা কি করি, আমরা impatient হয়ে যাই। ধরো আমরা কোনো উইন্ডো ক্লোজ করতে চাইছি, ওই ক্রস বাটনটায় আমরা ক্লিক করলাম, রাইট? সো if the response time is very high, ক্রস বাটনে ক্লিক করছি, বন্ধ হয়নি, তখন আমরা কি করব? আরো 10 বার ক্রস বাটনটায় ক্লিক করব। বা ওয়ার্ড চালাতে যাচ্ছি, মাইক্রোসফট ওয়ার্ড চলছে না, আরো 10 বার আমরা ক্লিক করে ফেলব। একটা সময় আসবে যখন হয়তো সেটা রান করবে, কিন্তু তখন দেখবে 10খানা উইন্ডো তৈরি হয়ে গেছে। ওকে, তো এরকম ভাবে তাহলে রেসপন্স টাইমটা কিন্তু মিনিমাম হওয়া উচিত। So the scheduling should be such that the response time should be minimum. So these are the different criteria. CPU utilization, it should be maximized. Throughput, it should be maximized. Throughput means the number of tasks finished per unit time. Turnaround time is the amount of time a process actually spends in the system. Okay, so that is turnaround time. Turnaround time should be reduced. Waiting time is the amount of time process has been waiting in the ready queue, right? And response time, amount of time it takes from when a request was submitted until the first response is produced. That is response time. Okay. Okay. So in the context of that, say, process transition diagram, say a new state to ready state to I'm writing it as execution state in place of running in order to avoid confusion with 2 R's here, right? So from E, waiting state, and then finish. So when a process enters into the system, this time, and when a process finishes, this time is called the turnaround time. Amount of time to execute a particular process. Then CPU utilization, so there may be a number of processes in the system. So if the system executes for say 100 time minutes, among that 100 time minutes, how much time the CPU was kept busy, or how much time the CPU actually executed. Okay, so that gives us the CPU utilization amount. Throughput, the number of processes executed per unit time. So take example of this thing. So say a banking system. Okay, so bank opens at 10 a.m. in the morning and closes at 4 p.m. And you have gone to this bank, and there in the bank you have entered at say 11 a.m. right? So you have entered the bank at 11 a.m. Then you stood in a queue for say for certain tasks, say updation, you want to update your passbook, so there is a queue in front of that say window. Then so there you had to wait. So there was a waiting time, and you were serviced at say 11:30. Okay, so 11:30 to and that printing of your passbook that took only 2 minutes. So 11:30 to 11:32. Then you required another thing, so you have to withdraw money. So you stood there in another queue in front of another window. Then so from 11:30 to say you had to wait till 12 okay p.m. And from 12 p.m. to 12 say 5 uh, you actually got the service from that person, and you got your money and you left immediately. So what is the turnaround time? Turnaround time is 12:05 minus 11. So turnaround time is 65 minutes, right? And among these things, the waiting time was what? Waiting time was from 11 to 11:30. So waiting time was 30 minutes here. Then 11:32 to 12. So here we have 20 minutes. So 28 minutes rather, 28 minutes. So total 58 minutes. 58 minutes you had to wait. And if I consider this thing as the time that you have used the banking personnel, so banking personnel were involved here for 2 minutes and 5 minutes. So CPU time was 7 minutes. Okay. Okay. So in this way, this is the characteristics for one process. This is characteristics for you, say process P1. So there may be other customers. So in the whole time, so from 10 a.m. to 4 p.m. banking time, the bank actually served, say, for example, say it served 100 customers, or say 400 customers. 400 customers, total time was what? 400 customer, total time was 10 a.m. to 4 p.m., 6 hours. So 6 hours, 6 into 6 is 360. So 360 minutes. So it would be this many tasks per unit time. Okay, so that is the throughput. Okay, so this is 6 hours. So this many customers per unit time. And your CPU utilization would be determined by this, how much time those banking personnel were kept busy. Okay, so based on that, so they actually perform this sort of task and this sort of task and this sort of analysis at the day end or the month end. Based on that, they may decide that they need to increase number of windows, or they may, if they cannot increase number of windows, they may restrict the number of customers that enter into the bank, and so on. And this sort of analysis is also performed by, say, different, say, healthcare facilities like the hospitals. They also do this sort of analysis. If they have built, say, operation theaters, say, expensive operation theaters, they would try to determine what is the utilization of that operation theater. So they would expect that this OT, operation theater facility, is used 100% utilization. So that's why you will often hear that, say, operation is scheduled at midnight, operation is scheduled at, say, in the very early morning, and so on. So this schedule is the objective might be to increase the utilization. Okay, if you have resources, then your object scheduling should be such that your resource utilization should be maximized. Okay, so we'll look into that different scheduling strategies, which actually tries to say optimize the different criteria. So this turnaround time should be minimized waiting time should be minimized, response time also should be minimized, CPU utilization should be maximized, and throughput should be maximized. Okay, so the basic scheduling strategy is first come, first serve. Whosoever comes first would be scheduled first. So let's take this example. So process P1, P2, P3, their CPU burst times are 24 unit, 3 unit, and 3 unit. And suppose they all come in this order, although they have all come at time 0, they have come in this order P1 followed by P2 followed by P3. The match chart for this schedule is, so they all have come at time 0. So when they all have come time 0, so first which process would be scheduled? The process which has come first, P1 has come first, so P1 would be scheduled first. It would be given CPU first, so it will use the CPU for 24 time minutes. Then process P2 would be given schedule next, it will execute for 3 time minutes. Process P3 would be given schedule next, it will execute for next 3 units. So this scheduling is typically described in a graphical manner using NAT charts, right? So starting from time 0 up to time 24, process P1 is scheduled. From 24 to 27, P2, 27 to 30, process P3 is scheduled, right? So if you try to determine what is the waiting time for the different processes, waiting time for process P1, its waiting time is what? Process P1 actually came at time 0 and it was giving the CPU at time 0. So waiting time for process P1 is 0. Waiting time for process P2 is, it was given CPU at 24, it came at 0, so waiting time is 24. And for process P3, it was given CPU at time 27, but it came at time 0, so its waiting time would be 27. So average waiting time would be 0 plus 24 plus 27 divided by 3. So this is equal to 70. Right? Whereas for the same set of processes, if they arrive in a different order, so they all have come at time 0, but they have come in this order, P2 followed by P3 followed by P1. So first P2 would be scheduled. So P2 is scheduled at time 0, P3 is scheduled at time 3, and P1 is scheduled at time 6. So now this waiting time for P1 would be what? P1 arrives at 0, it is given CPU at time 6, so waiting time of P1 would be 6. Waiting time of process P2 would be what? It has come at 0 and it was given CPU at 0, so it would be 0. And waiting for process P3 would be, it has come at 0 and it is given CPU at time 3, so it would be 3 minus 0, 3. So average waiting time would be 6 plus 0 plus 3 divided by 3, so that would be 3. So now the average waiting time has drastically reduced. The reason was that a large process, if it is in front of the queue, then average waiting time for all other processes will increase. Okay. So in the banking example, so if there is no, typically in different branches, there is a limit on number of instruments that it can provide to the banking personnel at any point of time. So if you, so they say that you can only encash 2 checks per person. Okay. Okay, so if this sort of limit was not there, if a person with 100 such checks is in front of the queue, that person will consume, say 100 checks may require 1 hour or 2 hour time. And all the people standing behind that person will have to wait that 1 or 2 hour time. That would be added. Okay, so average waiting time will drastically increase. Whereas if I have all the short processes in front, then average waiting time will decrease. right? So FCFS, this is one such effect which is called convoy effect. If short processes are behind long processes, then we call it as convoy effect. Okay, like say if we have a VIP convoy in front of us and that VIP convoy is actually moving very slowly, then even if we can drive much more faster than that VIP convoy, speed of that VIP convoy, we cannot drive first. Okay, so the average waiting time will increase for all the vehicles which are behind the VIP convoy. So that's why it is called the convoy effect. Or if you are behind a procession, মিছিলের পেছনে তুমি যাচ্ছ, মিছিলের পেছনে গাড়ি নিয়ে আছে, মিছিল যে গতিতে যাচ্ছে তুমিও সেই গতিতে যাবে বা তার থেকে কম, তার বেশিতে তুমি যেতে পারবে না। ওকে, সো দ্যাট ইজ কল্ড কনভয় এফেক্ট। যদি মিছিলের আগে চলে যেতে পারো তাহলে সব থেকে ভালো। Okay, so this is called convoy effect, which is seen in case of first come first serve scheduling, and we have a long process in front of all other shorter processes. Okay, so now we have another scheduling strategy which is known as shortest job first. In this case, we associate with each process the length of its next CPU burst. For each process, we associate the length of the next CPU burst and use this length to schedule the process with the shortest time. The process with the shortest next CPU burst, we schedule that process only. So the logic is very simple. We have a collection of processes right now which are ready for execution, and we'd like to know what is the length of the next CPU burst for each of these processes. And we'll select that process whose next CPU burst length is the shortest. Okay, and this shortest of first scheduling algorithm is the optimal. That means it gives minimum average time for a given set of processes. It is the best one. For a set of processes, the average waiting time is given by the shortest job first. Okay, so then you may ask, why at all we should have other scheduling algorithms if shortest job first gives the best average waiting time? The answer is that shortest job first scheduling algorithm is very difficult to implement because it's very difficult to determine what would be the length of the next CPU burst for each of the processes. So when you execute your program, do you specify what time your process would be executing? For general purpose operating system like say Windows, Linux, and so on, we need not give this info, or we do not give this sort of information, say about the amount of CPU time our processes will be taking, right? So that information is very difficult to obtain a priori. Before execution, it is very difficult to obtain. Okay. So we look into that how the a variant of SJF or SJF can be implemented using some approximation strategy. So before that, let's look into some example of shortest of first scheduling. So we have four processes P1, P2, P3, P4. Four processes. Their burst times are CPU burst times are 6 time minute 873. So they all arrive at time zero. So at time zero, the CPU scheduler looks into all these processes. They are present right now in the ready state. And the shortest job is what? Shortest job is process P4. P4 is the shortest job. So it schedules process P4 for how much time? Time 3. Then the next shortest is process P1 and it schedules it for 6 time minutes. So from 3 to 9. And the next shortest is process P3 for 7 time minutes from 9 to 16, 7 time minutes. Then process P2 for 8 time minutes from 16 to 24, right? So we have total 24 time minutes and the processes they are scheduled in this manner. So if you try to find out the waiting time, so waiting time for process P1 would be what? Process P1 arrived at 0, but it was scheduled at time 3. So it would be waiting time would be 3. For process P2, it arrived at 0, it was scheduled at 16, so it would be 16. For process P3, it arrived at 0, it was given the CPU at 9, so it would be 9. And for process P4, it arrived at 0 and it was given the CPU at time 0. So its waiting time is 0. So if you take the average, you will get this average waiting time 7. Right? So this is how SJF works. So this sort of SJF, this is non-preemptive version of SJF. And SJF can be preemptive and non-preemptive. So we'll look into that later on. But from the principle of SJF, as you can see, we need to know what would be the length of the next CPU burst. Based on that, we'll be choosing that process whose next CPU burst length is minimum or the shortest. Okay, so let's see how we can implement SJF. So we cannot have exact information about the next length of the next CPU burst. Rather, what we can have some estimate of the length of the next CPU burst. It shows similar to the previous one. They pick the process with the shortest predicted next CPU burst. So now what we do, we predict what would be the length of the next CPU burst. So can be done by using the length of the previous CPU burst using exponential averaging. So assume that a process starts with this, so as I have already told, a process starts from time 0. So let's assume that this is time 0 and this is the time axis. So it starts with a CPU burst. Say this is CPU burst 1. Then we have say probably IO burst, and then again we have CPU burst 2. Okay, then CPU burst 3. We have CPU burst 3 and so on. Okay, so what we try to do, we actually try to predict what would be the next CPU burst. So assume that the process has executed up to CPU burst 3. So based on this execution history, we will try to determine what would be the length, or we try to predict what would, before execution, we'll try to predict what would be the length of the next CPU burst or the length of the CPU burst 4. Okay, so assume that we have already executed up to this point. And based on this execution history, we'll try to predict what would be the length of the next CPU burst or the fourth CPU burst. So we define it like this. The length of the n plus 1th CPU burst. So this is tau. So length of CPU burst, we represent it using tau. N plus 1th CPU burst length would be equal to alpha times the actual length of the nth CPU burst, that means the previous CPU burst, and 1 minus alpha times the nth predicted CPU burst. Okay. Okay. So that means the fourth CPU burst, so tau 4 would be equal to what? Tau 4 equal to alpha times the actual length of the third CPU burst plus 1 minus alpha times the predicted length of the third CPU burst. কারণ দেখো এর আগেও হয়েছিল, তখন আমরা থার্ড সিপিইউ বার্স্টটাকে প্রেডিক্ট করার চেষ্টা করেছিলাম। সো প্রেডিক্টেড length of the third CPU burst was tau 3, but actually it was T3. Okay. Similarly, tau 3 was predicted in terms of the previous CPU burst. So tau 3 was equal to alpha into T2 plus 1 minus alpha into tau 2. Okay, so tau 2 was predicted length of second CPU burst, and this was prediction, but the actual was T2. Similarly, for tau 2, it would be alpha times T1 plus 1 minus alpha times tau 1. So tau 1 was the first predicted CPU burst length, predicted length of the first CPU burst, and T1 is the actual length of the first CPU burst. Okay, and tau 1 is what? Tau 1. So when execution for a program actually starts, so tau 1, the program hasn't started yet. So we have to predict what would be the length of the first CPU burst. So tau 1 would be some system-wide constant. Okay, some constant. So I'd be predicting for the first CPU burst, I would be predicting, say, so it would be 10 millisecond, but actually it was 12 millisecond. So it would be alpha multiplied by 12 plus 1 minus alpha into 10. Then we'll get tau 2, and we'll place that value tau 2 here, and we'll have predicted value of tau 3 in terms of tau 2 and T2. Okay, and so on. So in this way, we can predict what would be the length of the next CPU burst. Okay. Okay, and this alpha is some value which is greater than equal to 0, less than equal to 1. Okay, so what's the formula? Tau n plus 1, this is equal to alpha times actual length of the nth CPU burst, 1 minus alpha times predicted length of the nth CPU burst. So if alpha is equal to 0, tau n plus 1 is equal to tau n. If alpha is equal to 1, put 1 over here, so in that case tau n plus 1 is equal to Tn. So in this case recent history does not count. So আগের যা prediction ছিল সেটাই next prediction কিন্তু, আর এখানে recent historyটা count করছে, লাস্ট যেটা অ্যাকচুয়াল হয়েছিল সেটাই আমি নেক্সট এর প্রেডিকশন করছি। So in this way, if we expand the formula, so the formula tau n plus 1 equal to alpha Tn plus 1 minus alpha tau n, put the value of tau n here, so you would get what? This sort of expressions is both alpha and 1 minus alpha less than or equal to 1, each successive term has less weight than its predecessor. So we have both these, they are less than 1. So multiplication of two values which are less than 1. And then we have this is the jth term. So each successive terms will have a less weight, right? So that is why it is called exponential averaging. So we are predicting the n plus 1th CPU burst in terms of actual length of the nth CPU burst, actual length of n minus 1th CPU burst, actual length of n minus a, and so on up to tau 0, the predicted first CPU burst, and so on. Okay, so this is one method which can be used, adopted by the systems to implement shortest job first. Okay? This exponential averaging. So shortest job first It's a preemptive version. Preemptive shortest job first is called shortest remaining time first. Okay, so let's take one example of that. So we have process P1, P2, P3, P4. Their arrival times are not all zeros, so that they have arrived in this time and their burst times are given. So at time zero, which process is there? Only process P1 is there at time zero because it has arrived at time zero. Okay, so we have process P1, sorry, only process P1 is there. So P1 is scheduled. At time 1, another process arrives, P2. So at time 1, process P1, what is the remaining time of process P1? P1 total burst time is 8. It has executed for 1 time unit, so its remaining time is 7. And process P2, it has just arrived, so its remaining burst time is 4. So which one is minimum or shortest? P2. So P2 would be scheduled. At time 2, we have process P1 whose remaining time is 7, process P2 whose remaining time is 3, and new process arrives, process P3 whose remaining time is 9. So which one is shortest? P2. So P2 will continue. At time 3, at time 3, we have process P1 whose remaining time is 7, process P2 whose remaining time is 2, process P3 whose remaining time is 9, and another process arrives at time 3, which is process P4 whose remaining time is 5. So minimum is what? Process P2. So P2 continues. So P2 will continue up to this point. So at time 5, we have 3 processes, P1 with remaining time 7, P3 with remaining time 9, and P4 with remaining time 5. Which one is the shortest? P4. So P4 would be scheduled for 5 time minutes. So it will execute for 5 time minutes. So it will execute up to 10 time minutes. At time 10, we have process P1 and process P3. Process P1 with remaining time 7, P3 with remaining time 9. So P1 would be scheduled as because this is the shortest at that point of time. So P1 is scheduled for 7 time minutes, so 10 to 7. At this point of time, at time 17, we have only one process left, P3, whose remaining time is 9. So it would be scheduled from 17 to 26. So in this way, these 3 processes would be scheduled, right? If you try to find out what would be the average waiting time for this set of processes. So we have how many processes? We have 4 processes. So waiting time can be easily found out by this. Waiting time is equal to turnaround time minus the burst time. Okay, turnaround time minus the burst time. So for process P1, waiting time is what? So its turnaround time is what? It arrived at 0 and it finished at what? 17. So 17 minus 0 is the turnaround time for process P1 minus burst time. This is 8. So if I say, so I went to bank at 11 a.m., then I came out at 12, okay? And my burst time, that means interaction with the bank personnel, was 5 minutes. What is the waiting time? So just turnaround time is what? 12 minus 11, that is 60 minutes. And minus the CPU burst time, that 5 minutes. So 55 minutes was my waiting time. Simple. So in this case, waiting time for the first process would be 17 minus 8, that is equal to 9. The second process arrives at 1 P2. P2 is finished at this 5. So 5 minus 1, this is the turnaround time minus its burst length 4. So this waiting time is 0. P3, when did it arrive? At time 2, and it finished at 26. 26 minus 2, this is turnaround time 24, minus its burst time is 9. So it would be 24 minus 9, 15. And for process P4 finished at 10 and it arrived at time unit 3. Finished at 10, arrived at time unit 3 minus burst time. Burst time is 5. 7 minus 5, this is 2. Okay. So these are the waiting times. So average would be 9 plus 0 plus 15 plus 2 divided by 4. This would be 17 plus 9, 26 divided by 4. So this would be 6.5. 6.5 time unit is the average waiting time for this set of processes using preemptive version of shortest job first, which is called shortest remaining time first. Right? So with this, I will stop for a moment. So if you have any question, you can ask me right here.
স্যার বলছি ওই রিমেনিং টাইমটা আপনি কি করে ক্যালকুলেট করছেন বুঝতে পারলাম না, মানে ওয়েটিং টাইমটা বুঝতে পেরেছি, টিএ মাইনাস বার্স্ট টাইম। ও যেটা P1 P2 দিয়ে ওই যে গ্যান্ট চার্টের ওখানে লিখেছেন না, ওই যে P1 P2, হ্যাঁ
হ্যাঁ, রিমেনিং টাইমটা মানে কি? আমি রিমেনিং টাইম বলতে কি বোঝায়, যে একটা প্রসেস তার টোটাল বার্স্ট টাইম কত, আর সেই যদি এতক্ষণে এক্সিকিউট করে থাকে তাহলে তার রিমেনিং, হ্যাঁ ধরো প্রথমে যখন এসছে P1 এর রিমেনিং টাইম কত ছিল, ওর 4 হচ্ছে টোটাল, সরি 8 হচ্ছে টোটাল টাইমটা, 8ই ছিল, রাইট? at time 0 প্রথমে P1 এর রিমেনিং টাইম কত ছিল, 8 ছিল। এই যে P1 কখন এসছে, টাইম 0 তে এসছে, ওর বার্স্ট টাইম কত, 8। তাহলে ওর রিমেনিং কত আছে, কারণ ও তো আর এক্সিকিউট আগে করেনি, ওর বার্স্ট টাইম 8, আগে এক্সিকিউট করেনি, তাহলে ওর রিমেনিং হচ্ছে 8, রাইট? এরপরে দেখো 1 সেকেন্ড পর, 1 টাইম ইউনিট পরে যখন আরেকজন এসছে, কে এসছে, P2 এসছে, সেই সময় P2 রিমেনিং কত, P2 রিমেনিং হচ্ছে 4, কারণ ওর বার্স্ট টাইম 4, কিন্তু ও আগে এক্সিকিউট করেনি, কিন্তু P1 ওর বার্স্ট টাইম একটা টাইম ইউনিট এক্সিকিউট করে নিয়েছে এখানে, তাহলে ওর রিমেনিং টাইম কত, 7। ঠিক আছে? তাহলে একটা পয়েন্টে তোমাকে প্রত্যেকটা প্রসেসের রিমেনিং টাইম গুলো বার করতে হবে। P1 এর রিমেনিং টাইম 7, P2 রিমেনিং টাইম 4। এই পয়েন্টে টাইম ইউনিট 2 তে P1 এর রিমেনিং হচ্ছে 7, P2 রিমেনিং হচ্ছে 4 ছিল, তার থেকে এক টাইম ইউনিট অলরেডি এক্সিকিউট করেছে, তাহলে এটা হচ্ছে 3। আর P3 নতুন প্রসেসটা এসছে, তার তো তোমার রিমেনিং টাইম এটাই 9। এইভাবে প্রত্যেকটা অ্যারাইভাল টাইমে কিন্তু আমরা এই রিমেনিং টাইম গুলো বার করেছি। কেন বার করেছি? তার কারণ হচ্ছে যখন কেউ আসছে, তাহলে আমি দেখবো যে নতুন এসছে তার যে রিমেনিং টাইমটা, যে এক্সিকিউট করছে বা সিস্টেমে মানে যে এক্সিকিউট করছে তার থেকে ছোট কিনা, তাহলে যে এক্সিকিউট করছে তাকে আমি প্রিএম্প্ট করে যে নতুন এসছে তাকে আমি শিডিউল করে দেবো। যে ঘটনাটা ঘটলো এই ক্ষেত্রে P1 এক্সিকিউট করছে, P2 যখন এই 1 টাইম ইউনিটে অ্যারাইভ করলো, P2 রিমেনিং টাইমটা P1 এর থেকে ছোট, তাই জন্য P1 কে বললাম তুমি থেমে যাও, এখন P2 কে আমি শিডিউল করলাম। ঠিক আছে? এইটা যেভাবে আমি বলেছি, এইটা আরেকবার তোমরা বাড়িতে করার চেষ্টা করো। এই ধরনের এক্সাম্পল আমরা আরো অনেক করব পরে।
স্যার, হ্যালো স্যার,
শুনতে পাচ্ছি, বলো। হ্যাঁ,
হ্যাঁ
শুনতে
স্যার
পাচ্ছেন?
বলছি কি,
হ্যাঁ, শুনতে পাচ্ছি।
হ্যাঁ স্যার বলছি যে P1 আর P2 এর ক্ষেত্রে যেমন আমরা রিমেনিং টাইমটা মানে এখানে দেখালাম যে এক এক করে কমে গেল, কিন্তু স্যার তাহলে মানে P1 P2 পরে তো P3 P4 এসেছে, তাহলে স্যার ও মানে P3 আর P4 এর ক্ষেত্রে ওখানে রিমেনিং টাইমটা কমলো না কেন স্যার? এটা আরেকবার একটু বলে দিন না।
P4 এর এই P2 এর কিন্তু রিমেনিং টাইমটা কমেনি। কখন? দেখো, P1 এর রিমেনিং টাইমটা কত ছিল? 8 ছিল
হ্যাঁ
প্রথমে, একেবারে প্রথমে। এই যখন টাইম ইউনিট 1 হলো তখন P1 এর রিমেনিং টাইম কত?
7।
7 হলো। কেন 7 হলো? কেন 7 হলো? কারণ এই যে P1 অলরেডি এক্সিকিউট করেছে তো 1 টাইম ইউনিটের জন্য।
আচ্ছা
আ- আবার এই টাইম ইউনিট 1 এ P2 অ্যারাইভ করেছে, P2 অ্যারাইভ করেছে, তার রিমেনিং টাইম কত? 4। এইটা 4টা এখানে দেখানো। এইটা হচ্ছে অ্যাট টাইম ইউনিট 1 এ কি পরিস্থিতি সেইটা দেখানো। টাইম ইউনিট 2 এ কি পরিস্থিতি? P1 এর বাকি আছে 7, P2 এর বাকি আছে 3, কারণ P2 এক্সিকিউট করেছে এখানে। এই যে P2 দেখানো আছে, P2 এই টাইম ইউনিটটা এক্সিকিউট করেছে।
আচ্ছা
তাই জন্য ওটা 4 থেকে 3 হলো। আবার নতুন যে অ্যারাইভ করেছে P3, তার কত বাকি আছে? 9। সে 9 লিখলাম সেটা। এই পরিস্থিতিতে at টাইম ইউনিট 2 তে কি সিস্টেমের পরিস্থিতি সেটা আমি এখানে দেখাবো। সিমিলারলি এই টাইম ইউনিট 3 তে সিস্টেমের কি পরিস্থিতি সেটা এখানে দেখাবো। কারণ দেখো, প্রসেস P4 অ্যারাইভ করছে টাইম ইউনিট 3 তে, তার আগে কিন্তু আসেনি। তো
না
সেখানে দেখানো হয়েছে P1 এর বাকি আছে 7, P2 এর বাকি আছে 2। কারণ P2 দেখো, আহ, এই যে 2 টাইম ইউনিট এক্সিকিউট করেছে, 1 প্লাস অ্যানাদার 1 2, তাহলে 4 থেকে 2 বাদ দিলে 2 হচ্ছে। P3 এর হচ্ছে 9 আর P4 এর হচ্ছে 5। এইভাবে যখনই কোনো নতুন প্রসেস অ্যারাইভ করছে তখন আমরা প্রত্যেক প্রসেসের টাইমটা নতুন প্রসেসটা আসছে তার টাইম যদি তার রিমেনিং থেকে ছোট হয় তাহলে তাকে প্রিএম্প্ট করবে।
আচ্ছা স্যার।
ঠিক আছে?
হ্যাঁ স্যার ঠিক আছে।
Okay. Shortest of course. Now, another scheduling algorithm is other two that would be discussing is priority scheduling. So in this case, every process is assigned or is associated with a number which is called the priority of that process, and it's a integer value. The CPU is allocated to the process with the highest priority. So at any point of time, if say n number of processes are present, so among those n number of processes, the process with the highest priority would be given the CPU next. The strategy is very simple. Okay. The in many of the systems, they consider priority as the smaller the integer value, the highest the priority is. So that means a process with priority value 0 has the highest priority. So this sort of convention is followed in most of the Unix-like operating systems. So this priority scheduling can be preemptive or non-preemptive. Okay? So shortage of first priority scheduling is a kind of priority scheduling where we can consider that the priority of a process is inversely proportional to the length of the next CPU burst. If a process's CPU burst length is short, that means its priority would be high. or the process with the shortest next CPU burst length will have the highest priority. Okay, so SJF is, we can consider this as a kind of priority scheduling strategy. So the problem with priority scheduling is that there may be some condition which is called starvation. Okay, so a low priority process never get a chance to execute. So assume that we have a low priority process, but there is a constant supply of high priority processes. So all those high priority processes, they are getting scheduled. That means they are given the CPU, but the low priority process is not getting a chance to get the CPU. So in that case, we call it as starvation. So in order to solve this problem of starvation, we have one technique which is known as aging. Okay, as time progresses, we increase the priority of the process, even though the priority of the process is the lowest. As time progresses, say every 1 hour, we increase the priority of the process by 1. So if we adopt this strategy, then it is guaranteed that at some point of time it would have the highest priority, so it would be able to execute at that point of time. So aging is one solution to this starvation problem, which is same in case of priority scheduling. So let's take one example. So we have this process P1, P2, P3, P4, P5, and these are the burst times, CPU burst time corresponding to these processes, and these are the priority of those processes. Okay, and lower the value, priority value, higher the priority is. So priority value 1 is the highest priority, and priority value 5 is the lowest priority. Okay, so at time 0, among all those processes which are present right now, which process has got the highest priority? This is process P2. So process P2 would be scheduled for how much time? For the time that it requires. Its burst length is 1, so it will be scheduled for 1 time in it. At time 1, among the remaining processes, which one has got the highest priority? This is process P5, right? Process P5 will be scheduled for 5 time minutes from time 1 to time 6. Then at time 6, among the remaining processes, which process has got the highest priority? It is process P1. Process P1 will be scheduled for 10 time minutes. So 10 time minutes followed by process P3. Its priority is next 4, and then followed by process P4. Okay. So the waiting time, all the processes they have arrived at time, all the processes they have arrived at time 0. So waiting time for process P1 would be what? Waiting time. How can we find out waiting time? So first of all, find out the turnaround time. Say turnaround time. Turnaround time. This means when it has finished minus the arrival time. So it has finished at time 1 and arrival time is 0. So this is 1. For process P2, sorry, this is for process P1. Right. So process P1. For process P1, it has finished at time 16 and it has arrived at time 0. Process P2, it has finished at time 1 and arrived at time 0. Process P3, finish time is 18, arrived at 0. Process P4, finish time is 19, arrived at 0. Process P5, finish time is 6, arrived at 0. So these are the turnaround time. So waiting time would be what? Turnaround time minus the burst time. So it would be 16 minus 10, it would be 6. This is 1 minus 1, it will be 0. This is 18 minus 2, this is be 16. 19 minus 1, 18, 6 minus 5, this is 1, right? So these are the waiting times. So average waiting time would be 6 plus 0 plus 16 plus 18 plus 1 divided by 5. 41 by 5, so it was 8.2. Okay, so priority scheduling, the process that would be scheduled next is having the highest priority. And we have priority values associated with each of the processes, and typically in Linux-like operating system, it is considered that the process having the lowest priority value has got the highest priority. Right. So next is another scheduling strategy which is called round robin. So each process gets a small unit of CPU time. We call it as time quanta. So Q amount of time is given to each of the processes, and usually this length is 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. Say if you have say 4 number of processes, then in a round robin fashion, each of these processes would be given Q amount of time. Say process P1, Q amount of time, then process P2, Q amount of time, process P3, Q amount of time, process P4, Q amount of time. Then again, after that, another round, P1, P2, P3, P4, assuming that they have not finished. Okay, so if there are n number of processes in the ready queue and the time quantum is q, then each process gets 1 n of the CPU time in chunks of at most q times at once. So we have in our example, we have 4 number of processes. We have 4 number of processes right here. So total time would be 4q, right? So out of 4q, each process would be given q amount of time. Okay, so that is each is 1/4 of CPU time. Okay, so if we have here equal 4. So each process is given 1/4 of the CPU time, and whatever the process is given the CPU, it would be given CPU for q amount of time. So after executing q amount of time, again a process has to wait for how much time? So again a process would be scheduled here. After P1 finishes here, again it would be scheduled at this point of time, and it has to wait for 3q amount of time. So this is n minus 1 into q. So no process has to wait more than n minus 1 into q time unit. So after it has been given CPU for q amount of time, a process has to wait no more than n minus 1 into q amount of time. Okay. After that, it is guaranteed that it will again get the CPU and will execute. And there is some timer hardware which actually quantum time to schedule the next process. So whenever a timer device is there, it is given, it is configured to generate timer interrupt every q unit time, right? So whenever a process starts executing, the timer also starts. After q elapses, q time unit elapses, a hardware interrupt would be generated, and the currently running process, it would be preempted, and the next process would be given the CPU. The performance of this round robin actually depends on the value of this time quanta q. If q is very large, then it becomes FIFO, first come first serve. So q is very large means if q is larger than the largest time as a CPU burst of all the processes, then it becomes FIFO. Or if q is very small, then q must be large with respect to the context switch. So if q is very small, there will be frequent context switch from one process to another process. So it coming to this point as we discuss one example. So in this case, we have process P1, P2, P3. Their burst time is 24, 3 and 3, and time quanta is 4. So every process would be given 4 time unit in a round robin fashion. Process P1 is given 4 time units, so it executes for 4 time units. Then process P2 is given 4, but it requires how much? It requires only 3, so it finishes at 7. So at this point of time, process P3 would be given 4 time unit, but it requires how much? It requires 3 time units, so it would finish at time 10, right? Then process P1 again would be given for 4 time units. P1 again 4 time units, 4 time units, 4 time units, and 4 time units. Okay. So in this case, if the time quanta is larger than the largest burst time, if the time quanta is 30, then it is actually eventually it's a first come first serve. So P1 would be given 30 time units, so P1 will finish execution by that time, then P2, then P3. So it's a first come first serve. But whereas if Q is very small, so Q is assume it is 1 time unit. So there will be number of context switches would be very high. So P1 then followed by P2, P3, then again P1, P2, P3, P1, P2, P3, then P1, 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 and so on. So in this case, number of times the processor should switch context from one process to another process is very high, and the context switch time is not negligible, then would be having considerable system overhead, right? Uh, but the round robin scheduling has a better response time compared to other scheduling algorithms. It has got higher average turnaround time than is safe, so it's fast, but it has got higher response time. For interactive system, interactive means where the response time should be as minimum as possible. This round robin scheduling algorithm is used. And Q should be large compared to context switch time. And Q is usually in terms of 10 milliseconds to 100 milliseconds, where the context switch is less than 10 milliseconds, right? So process time is 10. Say processes burst time is 10. If the quantum is 12, number of context switch is 0. If the quantum is 6, number of context switch is 1. If the quantum is 1, number of context switches is 9. So this actually shows as it go on decreasing the quantum size, number of context switches increases. And turnaround time varies with the time quantum. So for a given set of processes, this set of processes, P1, P2, P3, P4, as we go on increasing the length of the time quanta, the average turnaround time actually varies like this. It's not a steady curve, it's either increasing or decreasing. So it actually increases from 1 to 2, then again decreases, then increases when the time quanta increases from 3 to 5, and then again it decreases. Okay, and from 6 to 7 there is no such change. So again the average turnaround time for it, it would depend on the given set of processes. So for this given set of 4 processes, the average turnaround time has been such. Okay, so far we have studied whatever CMX strategy we have started. In that case, with the ready queue, there was a single ready queue. So ready queue contain actually all the processes which are in ready state. Now in multi-level queue scheduling, ready queue is partitioned into separate queues. Might be with the ready queue. So previously we had only one queue of processes, queue. Now we have two queues. One queue is for say foreground processes, those are interactive in nature, and another is a queue of processes which are background in nature, like say batch jobs or say number crunching applications, CPU bound jobs. So processes, they are permanently given the queue. So whenever they come to this ready state, they are either put into the foreground queue or the background queue, depending on say a priori knowledge about their nature. So whether they are interactive process or background processes. And each queue would be scheduled in a using different scheduling strategy. Like this foreground or interactive, they may be scheduled using round robin, and this background or batch jobs, they may be scheduled using FCFS. So the idea is that multi-level queue scheduling, ready queue is divided into partition into two different queues, and the processes, whenever they come into this ready state based on their characteristics, they are put into either this foreground queue or background queue, and different queues they are scheduled using different scheduling algorithms. And scheduling must be done between these queues also. This is important. Fixed priority scheduling in this case start all from the foreground, then from the background. So whatever time you have, first you give all your time here for the jobs which are there or the tasks which are there in the round robin queue, sorry, or the foreground queue. When all the processes in the foreground queue have been serviced, then only you schedule processes from the background queue, right? Time slice, each queue gets a certain amount of CPU time which it can schedule among its processes. So this is fixed priority. So first one of the queue would be scheduled, all the processes when they finish, then the other queue would be scheduled. In case of time slice, so if say total 100 unit of time, say 80 unit of time would be used by this all these processes belonging to the foreground queue, and 20 unit of time would be used by all the processes which are there in the background queue. Okay, so this is time slice and another is fixed priority. So whatever time you have CPU time, you are dividing it based on in the ready state. Okay, so multi-level queue. So we talked about two queues. We can have other different queues also. Say highest priority queue, system processes, interactive processes, next priority, then interactive editing process, batch processes, student processes, they are given the lowest priority. So we have these multiple queues in the ready state. So, and whatever time we have, we can either have fixed priority, that means when all those higher priority processes have finished, then only student processes would be given the CPU. Otherwise, we can have, say, this thing, time slice. So, out of say 150 time unit would be given here, then 20 time unit here, 10 time unit here, 10 time unit here, and 10 time unit here, and so on. For example, multi-level feedback queue. In this case, a process can move between various queues. So we have multiple queues. Okay, this is one queue, multiple queues. But the processes, whenever they enter into the ready state, they are assigned a fixed queue. So either this first queue or second queue. But in this case, feedback queue, a process can move between queues. So a process can move between the various queues. Aging can be implemented this way, right? So we'll take one example. So multi-level feedback queue scheduler defined by the following parameters, like the number of queues we have, scheduling algorithms for each queue, method used to determine when to upgrade a process from low priority queue to high priority queue, or when to demote a process from high priority queue to low priority queue, and method used to determine which queue a process will enter when that needs service. Okay, whenever that process enters into the ready state, which queue that process will enter. Okay, so let's take one example of this multiple level or multi-level feedback queue. So we have three processes, Q0, Q1, and Q2. So this is Q0. Whenever a process enters into the system or enters into a ready state, it would enter into the Q0. Okay, and Q0 is served using round robin time quanta 8. Time quantum is 8. So whenever a process enters, it would be given time quanta 8. If the length of the process is less than 8, then it would finish and exit from the system. But if its burst time is greater than 8, then it would be put into the next queue. Next queue, here also we have round robin with burst time 60, quantum time quantum is 16. So if the process length is says, say 20, total length was 20. So in this queue, it was given 8 time unit. After that remaining 12, it would be given 16 time unit. It would use 12 and it will finish and it will come out of that. But if the length of the process is more than 24, 8 plus 16, 24, then it would be moved to the third queue, Q2. Here it would be scheduled using FCFS. So a new job enters Q0, which is start round robin. When it gains CPU, job receives 8 milliseconds. If it does not finish in 8 milliseconds, job is moved to Q1. Then Q1 job is again served using RR and receives 16 additional milliseconds here. And if it still does not complete, it is preempted and moved to the Q2, right? So a process, if its length is less than 8, it would come to Q0 and will exit from Q0, right from here. And if its length is more than 8, it will come back here and it will again, so it would go to Q1. Again, it would get 16 amount. If it is less than, if its length is less than 24, then it will finish right here. But if its length is greater than 24, then it will be moved to Q2. But here it would be scheduled using FCFS. So this is one example of a multi-level feedback queue, right? Okay, so with that I'll stop. So if you have any question on the scheduling chauffeur, so you can ask me right now.